Hello students. So in the previous class we introduced the concept of level surfaces, and we also saw two results that when you have a level surface on a region R, then at every point of R only one level surface that can pass through that point that point in R. And we also saw another result which says that gradient of a function is perpendicular to the surface f x y z equals to C. So, now that we have those two basic results, today we will start with the concept of directional derivative, and we will try to work out few examples based on directional derivative. So, we will start with a formal definition. What do they actually mean? So, directional derivative of a scalar function. All right. So, the formal definition goes like this: let f x y z defines a scalar field in a region R, and let P be any point in this region, and suppose Q is a point in this region in the neighborhood BUR, in the neighborhood of the point P, in the direction of a given unit vector. So, this is very important. We always have to have a unit vector when we are calculating the directional derivative of a given unit vector a cap. Then limit q tends to p, f q minus f p divided by p q, if it exists, is called the directional derivative of f at the point P in the direction of a cap, So, basically what it means is you have a point P on a surface f x y z equals to C in a region R, and then you have another point, let us say Q, in the neighborhood of the point P. So, when Q approaches to P, then if this limit exists, then this this limit is actually called as the directional derivative in the direction of this unit vector a cap. So, this point Q which we have chosen, so this point Q is of course is a point in the neighborhood of the point P, but it is also in the direction of a unit vector a cap. So, it is a point in the direction of a unit vector a cap, and then we calculate this limit, and if this limit exists, then we say that this limit is actually the directional derivative is the directional derivative of the function f at the point p in the direction of a cap. All right. So, basically what it means is so physical meaning, or what it means is interpretation. We can write interpretation of directional derivative. So, I write it as dd. So, interpretation is, let p be any point. So, what we are saying is, let p be any point x y z, and q be the point x plus delta x, y plus delta y, and z plus delta z. And suppose PQ, which is a very small arc length, is delta s. So, it is a very small arc length, and we assume that the length is delta s. All right. So, suppose PQ is equals to delta s, then delta s is a small element, at p in the direction of a cap. And if delta f is equals to f of x plus delta x, y plus delta y, and z plus delta z minus f x y z is equals to, so this is our point q, this is our point p. So, f q minus f p, then del f by del s represents the average rate of change, of f per unit distance in the direction of a cap. And now the directional derivative of f at the point P in the direction of a cap is basically limit q goes to p f q minus f p divided by p q is equals to basically limit q goes to p or delta s goes to 0, or we can write delta s goes to 0 del f by del s. So, this is nothing but our df ds, because when delta s goes to 0, this whole thing will converge to df ds, and it represents, so basically it represents the rate of change of f with respect to distance at p in the direction of a cap, which is a unit vector. So, what it means physically is that we have two neighboring points on the surface f x y z equals to c, and then that is small increment in the function f or from the point p to q is denoted by delta f and delta s. So, that small increment in the function f, we write it as delta f, which is basically f q minus f p, and the small element, which is this p q, is basically delta s. So, delta f by delta s, when delta s goes to 0, is actually the average rate of change of f per unit distance. So, how much the function is changing, how it is changing per unit distance is given by del f del s in the direction of the vector a cap. So, we always have a unit vector along which we are calculating the rate of change of the function f, and the directional derivative of the function f at p at this point p is basically when limit q goes to p, we write f q minus f p by p q, which is basically our del f by del s, and at the point p we have this delta s, this surface element is that a small element at the point p in the direction of a cap. So, that is what we are calculating here. So, this is basically our rate of change of the function f per unit distance in the direction of a cap at the point p. So, this is represents the rate of change of the function f with respect to distance or per unit distance at the point p in the direction of a cap. So, a cap is a unit vector at the point p, and this df ds is actually denoting our rate of change of the function f. So, this is what we mean physically by the directional derivative. So, at a certain point you have a unit vector and you need to calculate the rate of change of that function along that unit vector. So, that is what simple in simple words it means. So, you have a unit vector at a point p on a surface f x y z equals to c. So, your directional derivative is actually the rate of change of that function f x y z with respect to distance, of course, in the direction of that unit vector at the point p. So, or whichever point it is where you are calculating the directional derivative, and this is what we mean physically, or the physical interpretation of the directional derivative. Now, that we have stated df ds is basically that rate of change of f with respect to distance. How do we calculate the directional derivative? Do we really have to differentiate f x y z equals to c? So, do we really have to differentiate f x y z equals to c as del f del s, or do we have to calculate df ds to calculate the directional derivative, or is there any other formula to calculate the directional derivative? So, that we will now prove in terms of a small theorem. So, whether we calculate this thing or whether there is some other tool that will help us calculate the directional derivative. So, that we are going to that is something we are going to see now. So, let me put a small theorem here. So, today it is theorem 1, and it says that the directional derivative of a scalar field f at a point p x y z in the direction of a unit vector a cap is given by df ds is equals to gradient of f at the point p times a cap. So, we have to calculate the gradient of the function at the point p. So, I can put a p here, and that basically says that the gradient of the function has to be calculated at the point p times the unit vector a cap. So, that means instead of calculating df ds, we can just using this theorem, the directional derivative of the function f at the point p in the direction of a is given by gradient of f at the point p dot product with a cap. So, this df ds is equals to this. So, this df ds is equals to gradient of f at the point p times a cap. So, this is a very small result, and we will try to prove that and see how this thing this df ds equals to this gradient of f at p times a cap. So, the proof or the solution. So, let f x y z be a scalar field. So, let f x y z be a scalar field in the region R, and let p x y z be any arbitrary point in the region R. So, p x y z belongs to R. So, then I can write OP, or the position vector of the point P, is equals to x I y j and set k. All right. Now, if S denotes the distance of P from some fixed point, A in the direction of A cap, then delta x denotes a small element, at P in the direction of A cap. And therefore, dr ds is a unit vector at the point P in this direction, that is dr ds is equals to A cap. So, what we are doing is we are assuming the distance of P from any fixed point A in the direction of A cap. So, in the direction of A cap, we assume any arbitrary point, let us say A, and S denotes the distance. And then in that case, a small element or a small increment in the point P in the direction of A, then that small increment is denoted by delta x. So, if we are moving along the surface and from P to, let us say, Q, or P to A we are going, then that small increment is basically our delta x, then in the direction, and then in the direction of A, of course. So, therefore, dr ds, basically the rate of change of r with respect to the distance, is a unit vector in the direction of this unit vector A cap. So, this basically dr ds is a unit vector at the point P in the direction of A cap. All right. So, but our r is equals to x I plus y j plus z k. So, from here our dr ds will be dx ds times I, dy ds times j, and dz ds times k. All right. So, now our gradient of f times A cap, what is this? So, this one will be del f del x times A1, and then del f del y times A2, and del f del z times A3, right. So, this A actually, so this A1, A2, A3 will be actually, we can write it now. So, dr ds is basically dx ds from here, dy ds and dz ds. Now, dr ds is equals to A cap. So, that means if I write this one as A cap, so the components of A cap will be A1, A2, A3. So, A1 equals to dx ds, A2 equals to dy ds, and A3 equals to dz dx. So, I am substituting them here. So, del f del x times dx ds, and this one will be dx ds, and this one will be del f del y times dy ds, and del f del z times dz ds. So, since dz and del z, they are a small element, so we can cancel this del del x del del x del x. So then this will be df del f del s, del f del y, and then del f. So del f del s, del f del s, and then this one again will be del f del s. So ultimately, if I multiply, so ultimately, so what I am trying to say is that we can write it something like this: 1 by ds, and then what I am trying to say is del f del x times dx, del f del y times dy, and del f del z times dz. So this is what we can do here. And now this is nothing but our df. So that's from differential calculus. This is our df. So I can write it as df ds. Now we know that df ds is the directional derivative at the point P in the direction of A. So that's what physically it means from the definition of directional derivative. So this is our directional derivative of the function f at the point P in the direction of A. So what we have is, we have df ds is equals to gradient of f times a cap. And if we want to calculate the directional derivative, then we can calculate the gradient of the function f at the point P, this is very important, times the unit vector A. So this is the required formula to calculate directional derivative. All right. So, and this is what we wanted to prove. So the directional derivative of a scalar field at the point P in the direction of a unit vector a cap is given in this fashion, and just assuming some basic results from the differential calculus, and not assuming but using those results from the differential calculus, we can be able to show that the directional derivative df ds is equals to gradient of f at the point P times a cap. And this is what is equal to our directional derivative. All right. So now we will try to work out few examples before we go to our next topic. So let's calculate the directional derivative or work out few examples on level surfaces. All right. So in the previous class we started with level surfaces, and in today's class we started with directional derivative. So we'll try to solve few examples on both of these two topics. So the first one is, first example, find a unit normal vector to the level surface x square y plus 2xz equals to 4 at the point 2, -2 and 3. So our given level surface is x square y plus 2xz equals to 4, and we have to calculate the unit normal vector at the point. So let's put a p here at the point P 2, -2 and 3. So what we are going to do, first of all, from the result on level surfaces, we know that gradient of f is a normal to this level surface. So here it says that find a unit normal. So we have to find a normal to this surface given here, and then dividing it with its magnitude will give us the unit normal. All right. So those two steps are clear. So first of all, we have to calculate its gradient. So here the equation of the level surface is fxyz equals to x square y plus 2xz equals to 4. All right. And we know that gradient of f is perpendicular or normal to the surface f, then first of all we calculate the gradient of f. Gradient of f would be gradient of x square y plus 2x z. Of course, gradient of 4 will be 0. So, calculating this one is not difficult. So, del x 2xy plus 2z times I plus del y would be x square j and del z will be 2x k. So, this is the required gradient of f, and now the gradient of f at the point P, and P is 2 minus 2 and 3. So, if I substitute then it will be 2 times 2 minus 2 plus 2 times 3 times I plus x square, which is 2 square times j, and this one is 2 times 2 k. So, this will be ultimately I don't know, minus 2i plus 4j plus 4k, and therefore, this gradient of f. So, the gradient of f, or minus of 2i plus 4j plus 4k is normal, is normal or perpendicular to the surface, is normal or perpendicular to the surface fx y z. All right, but we have to find out a unit normal or unit vector perpendicular to this. So, to give the unit normal, we write it as 4j plus 4k, and then we divide it by its magnitude. So, that means minus 2 square, which is 4, plus 4 square is 16 plus 16. So, ultimately this will be minus 2i plus 4j plus 4k, and then this will be 32 plus 40. So, we can write 2 square root of 10 is a unit normal or unit vector, unit normal or unit vector perpendicular to the surface fx y z equals to c, and fx y z is basically our x square y plus 2x z equals to 4. So, that c is 4. So, this is the required this is the this one is 16 32 plus 4 36. Okay, so this has to be 6, it's not 40, it's 36. So, it will be 6. So, this is the required unit normal perpendicular to the surface fx y z equals to c. And you see we had a equation of a level surface here in this example. We had a equation of a level surface. So, we wrote this level surface as fx y z equals to c, and then we had to calculate the gradient, because gradient is a vector normal to the level normal to the surface fx y z equals to c, and then we calculated the gradient at the point P, and then we divided it with its magnitude, and that gave us the unit normal or unit vector perpendicular to the surface x square y plus 2x z equals to 4 at the point 2, minus 2 and 3. You also have to make sure whether this point lies on that level surface or not, because we can do all this calculation, but always make sure that this point lies there. So, if I substitute there, then this will be 4, so minus 8, and that will be 4 12. So, of course, this point lies on the level surface. So, before you calculate anything, you also have to make sure the given point P lies on that level surface or not. So, here in this case it does lie on that level surface, and therefore, the gradient of f is actually normal to that level surface at the point P, and if you divide it with its magnitude, then that's the unit normal. Here I can write it as gradient of f cap. All right. So, today we saw one example motivated from the level surface and unit normal. In our next class, we will continue with the examples on level surfaces and directional derivative, just to make the concepts clear, and I look forward to you in your next class. Thank you.